organized. We have a sequential decision-making process. So we want to find a policy, a good way of choosing actions or making those decisions. And we're going to learn this policy by interacting with an environment. We're going to interact with that robot, or we're going to interact with that Go game to learn a good policy. And by interacting with the environment, we collect data. So initially, it's unlike many other, like supervised machine learning problem, initially we don't have any data in the classic reinforcement learning problem. And we interact with the environment and slowly get data and then use that data to make good decisions. And part of the problem also is, how do we interact with the environment? Because some data is more interesting than other data. So we want to interact in a way to collect interesting data. So again, as I mentioned now, what we want to do is maximize the expected return. And so this is a standard type of reinforcement learning equation. This is maximizing the discounted reward. So what we have here is we have time denoted by t, and at every given time step, we're in some state denoted by s of t, and we take an action denoted by a t. When we take that action, we move into a new state. Probabilistically, we'll move into a new state, st plus 1, and we'll also get a reward. And the reward is denoted by r st a of t. And in this version here, we're going to have the rewards are going to accumulate over an infinite period of time. And in order to, for a number of different reasons, but we're going to discount those rewards. And so, and this is sort of that, so at time t equals 0, we get the full reward. At time t equals 1, it gets discounted by gamma. Time t equals 2, it gets discounted by gamma squared, et cetera. And this pi here denotes the policy. It's the rule that we're going to use for choosing actions. And we want to choose this, this rule for choosing actions in order to maximize this expected discounted reward. And tau here just denotes the trajectory. It's essentially all the, by choosing a policy pi, that defines a probability measure over all possible trajectories. Trajectories consist of all the sequences st and at. So pi is very important here. It's the policy for choosing actions. Typically, the way we look at so-called stationary policies, so when we're in state S, according to in state S, we're going to choose some action A. We want to find that policy. And in general, we look at probabilistic policies or stochastic policies, where the policy is actually a distribution over the action space. So just a little notation here. So what is this this problem, reinforcement learning, which is very much related to so-called Markov decision processes, and dynamic programming. What is the problem with traditional reinforcement learning and dynamic programming? The big problem, why it never really was that useful. It was interesting, and we always just taught it in classrooms, but it never really saw the light of day in terms of applications. Was because of the curse of dimensionality. With Markov decision processes, dynamic programming, reinforcement learning, you can only solve problems with relatively small state spaces. As soon as the dimension of the state space becomes large, like 3 or 4 or 100 or what have you, the number of states becomes too big, and none of the algorithms become useful anymore. So one example that you could solve, for example, is playing blackjack. You can find the optimal policy for playing blackjack because blackjack is just a one-dimensional state problem. It's just you playing against the dealer, maybe 2 dimensions at most, depending how you arrange the states. But for other kind of problems, such as a problem like Go or chess, you would never be able to solve that by traditional reinforcement learning. So what happened then is, there was the developments of deep learning. And then people combine deep learning with reinforcement learning to get deep reinforcement learning. And all of a sudden, boom, we can solve all these really fast, interesting, large-scale problems. And I'm going to review some of those results now. And but before we do that, so I don't have to say too much about deep learning. I'll just have one slide here. I think we all know that most of us are in this room are probably quite familiar with deep learning, but it's just been phenomenal what's happened really in the past 10 years, and it's still happening. And this is really, we can really look at this as maybe this decade is the decade of deep learning perhaps. And I don't know if there's any other field, this is of course a very parochial view, but I don't know if there's any other STEM field that is profiting as much, that is exploding as much as this is as deep learning is right now. And so deep learning, of course, has been used initially with speech recognition, and it's been, of course, been used very successfully in machine translation. And it's been used, in all kinds of computer vision applications, including object recognition. And more recently, it's been used. There's been a lot of press in text-to-image work using diffusion models. And very, very recently, of course, there's been, this is in the press all the time, ChatGPT, which allows us to give a prompt and it returns an essay or even a computer program. And then and about 2 years ago, there was a major advance in computational biology with deep learning, with AlphaFold. And some people feel this is going to be one of the biggest scientific breakthroughs in computational biology ever. So and this is just, much of this stuff has just happened in the past few years. What's going to happen next year and 2 years from now and 5 years from now? It's very difficult to predict, but I think many great things are going to continue to happen. Okay, I'm not going to talk about this. I'm going to skip these slides. All right, so what is an example of a deep reinforcement learning algorithm? So this is one of the more basic, well-known algorithms. I'm just going to review it just to get the notation here. And this is a so-called the policy gradient algorithm. It's been around for a long time, and how does it work? So again, we have a policy, and the policy is going to be, we're going to use a neural network to define our policy. So the input to our neural network is the state of the system, whatever the state might be. And the output is a distribution of a finite action space. So we have like a softmax output that will have a distribution over a finite action space. So this is just, think of this thing as a neural network, pi theta, and that's our policy. So it's going to be a rule for choosing action. When we're in state S, we're going to choose an action A. We have a finite number of actions according to this probability distribution that's given to us by our neural network. And this here again, this is the expected return. There's no discounting in this equation. No need for discounting. Let's just say that the task is of finite length. The episode is an episodic problem, which is which comes to an end, like playing a game of chess will come to an end. And we want to, this is the total return that we get. So at every time step, we get some reward. And this sum here is the total return. This is the expected return. And the natural thing we want to do is change our policy, change theta, to increase the expected return. We want to do a gradient step. We want to modify theta, our policy, our neural network, to increase the expected return. Now, so how do we calculate this gradient? It turns out that there's this is one area where there's some nice theory. There's a very nice theoretical result which says that an unbiased estimator for this gradient is given by this thing here, where so when you're in state ST, G of t is the return from time t until the end of the episode. So it's all the rewards that you get until the end of the episode, and then it's times the gradient of a log of pi theta, where this is your neural network. So we can calculate this from backpropagation. So the algorithm, I'm not going to go through the proof, there's no need to do that, just give you a general sense of a typical VRL algorithm, is that we have our current policy, pi theta, we have our current neural network of our current parameters data, and we're going to run an episode. So we're in some state, we use our neural network to choose an action, and then after we choose an action, we give that action to the environment, we get a reward, and then we move to a new state. Then we move to a new state, we use our neural network to choose an action, we give that action to the environment, which might be the robot or the chess game, what have you. That moves us to a new state and gives us a new reward. And we keep on going, and eventually the episode terminates. And then, so we generate this episode, and then for each state S of t in this episode, we'll do an update. We'll calculate G of t, the return from state of S of t, and then we'll do an update like this. And this, under suitable conditions on the choice of the time step, we can even, it can be proved that this will converge to a local optimal. So anyway, that's just to give you an idea of an algorithm. Another thing that some of you who've looked at reinforcement learning, you've probably seen the so-called Q function, or the action value function. And that's defined as, again, just the total reward beginning in state S and choosing, so you're beginning in state S, you choose action A, then follow policy pi. So for the first step, you choose action A, and then after that, you follow policy pi. And many algorithms are based on this notion here, without getting into all the details, but many algorithms are based on this so-called action value function. And so in deep learning, well, when we use deep learning or deep reinforcement learning, another approach is to try to fit a neural network. This would be a different neural network whose inputs would be state S and A, and its output would be the Q value. And we try to fit that to approximate Q pi. And then if we do get a good fit, then what we would do in practice is after we fit Q theta, the action that we would actually take, the action we take would be the argument max of this guy here. So this is so the first approach that I spoke about was a so-called, could be called an actor approach, where we have the neural network is the policy. The second approach is what we sometimes call the critic approach, where the neural network is this Q function. And then there's actually a whole nother class of algorithms called actor-critic algorithms, where you have two neural networks. You have one neural network for the policy and another neural network for the Q function. And so again, this is just my brief, very high-level overview of deep reinforcement learning. So that's, without getting into, we can talk about deep reinforcement learning for an entire course. And we're not going I just want to introduce a little bit of notation, a little bit of terminology. If you're not familiar with all this, no need to worry. It's just, what's important is just get this general idea that, that we're using neural networks, and we either use the neural network to parameterize the policy or the Q function or both. There's algorithms in all three cases. So what are some of the recent breakthroughs in DRL? So perhaps the first big major breakthrough was in 2014. How many of you are familiar with this, the Atari game system? One of the one really big breakthrough in artificial intelligence. And here they use an algorithm called deep Q networks. And so here, what this was about was this happened at DeepMind, and they have these Atari games. You have an API that gives you access to these Atari games, and I believe there's like 49 of them. I can't remember the exact number. And the only thing that the algorithm sees, the algorithm doesn't know anything about the game at all, the rules of the game, no notion of a ball or anything. The only thing the algorithm sees is the pixels. So there's this a video game, so we have frames. It sees the pixels in the frames and the rewards, the points that it's getting. So the algorithm doesn't know anything more than that. And the algorithm then, the goal is to get this reinforcement learning algorithm to learn to play the game. And so the algorithm there's actions that you can take, like you can move the cursor to the left or the right. And initially, in these deep reinforcement algorithms, because the neural network is initialized with random weights, it's just taking random actions. It's just doing random stuff. So at the beginning, it's really bad. But over time, it starts to see, oh, when the pixels are this way and I move my cursor to the right, I get points. When the pixels are this way, I move the cursor to the left, I also get points. And over time, it starts to learn through these algorithms the right way to move the cursor to say, hit the ball. Here's the hit the ball so that we can knock out bricks, for example. And this was a kind of, major, it's still kind of amazing, I find, that an algorithm can learn to play such a complicated game by just seeing pixel values and points that it gets from that it gets when it succeeds at doing something. So, so it achieved human level performance for many games, not all the games, but they were able to get it to achieve human level performance for about half of the Atari games using the same algorithm, the same neural network for all, and the same hyperparameters for all the games. Okay, you have to retrain it each time. It's different. When I say same neural network architecture, the parameters are different for different games, but otherwise everything else is the same. They don't have a parameterized policy. Instead, they have a parameterized queue network. The input is that they use 4 frames of pixels, the 4 most recent frames of pixels. That's the input. And the output is this estimate of the queue function. And then once they have this estimate of queue function, the action they take is just what I said before, is the argument max of the queue function. So the action, do I move the cursor to the left or to the right, or do I keep it where it is? It's just the argument max. There might be 3 or 4 different actions here. And the training, I won't go into details, but the idea is roughly the idea is to minimize the so-called Bellman error that you have in dynamic programming. So that was the first major breakthrough. The next huge breakthrough was, which received a tremendous amount of attention in the press, is AlphaGo, which was in 2016. And this uses a technique which I call deep Monte Carlo RL. So of course it was a grand challenge to an AI. It was a major grand challenge to be able to beat, come up with an AI algorithm to beat the grandmasters in Go, excuse me. And many people predicted that it was still another 20, 30 years away before deep learning came around. And all of a sudden, they were able to do it. And again, this came out of DeepMind. So there's just a huge number of states. Each state here is a board configuration. And then after the AlphaGo was the first one. Then subsequently, they published another paper, AlphaZero, which is a more elegant algorithm. And in AlphaZero, they train completely from scratch. There's no human expert demonstrations at all. So it's just like the Atari game. At the beginning, it's just taking random moves. You're doing random things and you're losing all the time. But you keep on training, you keep on training, you keep on training. And they train, in those days, they would train for about 2 days. And finally, they come up with a policy that they would use it to play against grandmasters. And they would beat the grandmasters. So, and so this algorithm has an outer loop and an inner loop. And both of them are using Monte Carlo ideas. So, so 2 Monte Carlo loops. In the inner loop, they use this thing called Monte Carlo tree search. How many of you have heard of that? Anyone here ever hear that? Monte Carlo, a few of you have heard of it. So Monte Carlo tree search was already being used in Go before this came around, but without deep learning. It was one of the main AI techniques for designing algorithms for playing Go, but it wasn't able to beat, by itself, wasn't able to beat the grandmasters. And it's basically a planning algorithm. It does something very similar to what we do when we play chess or Go. When we play chess, you're about to make a move, you usually think, right, well, if I move here, then my opponent's going to go there. And then if I go here, my opponent will go here. Or maybe if I go here, my opponent's going to do this. And then I'll go here, and my opponent will do that. So we build out this kind of tree in our head of possible moves. And Monte Carlo tree search kind of formalizes that kind of thinking. And so, so that's what they do in the inner loop. And in the outer loop, they actually just play games to completion. So you play the game entirely to completion. It's so-called self-play, in that both players, when you're designing these algorithms, are using the same algorithm. They're both going to be using the same algorithm. And so they play games to completion. That's the outer loop. And at the end of each game, for all the states that you have visited, you're going to update your value function. This is similar to the queue function. And so you're going to basically, so you're going to change without getting the details, you're going to use gradient descent, stochastic gradient descent, to modify the theta and move it in the direction that improves your estimate of the V function. So there's two loops. On the outer loop, on the outer loop, we play entire games, and then we improve our estimate of the value function. On the inner loop, as we're playing the game, we use Monte Carlo tree search to do this kind of planning strategy. The next, I would say, this one hasn't received as much press in the general press, as much attention, but a lot of people in academics have been working on this and elsewhere, a lot of research groups, and that's controlling robotic locomotion. And what people have been doing a lot is working first with a computer simulated robot. And this is the so-called Muchoko environments. And some of these Muchoko environments are quite complicated. And the state space is continuous and multidimensional. So the state space is no longer like in Go, finite. Go, it's finite, but astronomical. Now it's continuous and multidimensional. And also the action space is continuous and multidimensional because the actions are the forces that you place on the various joints, and those forces can have continuous values. And the goal is to try to train these robots so that they can stand up, you put forces on them just the right way, and run as fast as possible, and do that as quickly as possible. And this has been done mostly by so-called actor-critic algorithms, where we have a neural network for the policy, the actor, and also a neural network for the Q function, the critic. And some of the more famous algorithms are DDPG, TD3, SAC, and then we had developed an algorithm which we call RedQ, which is the state of the art. That is the SOTA algorithm for this particular problem. So, a couple more examples. Another recent, how many of you heard of this? This is very recent, 2022, matrix multiplication. Some of you have heard about this, right? Okay, many of you have. So here, this again is at a DeepMind. What they do is they use ideas from AlphaGo and AlphaZero to try to make matrix multiplication more efficient. Because we use matrix multiplication, not just in machine learning, but in many scientific applications. And it's desirable, if possible, to try to be able to do it more efficiently. And the idea here is that to try to come up with ways where matrix multiplication involves additions and multiplications. So we want to try to do it in such ways that most of the effort is in the multiplication. Addition doesn't cost too much. Most of the computational effort is in multiplication. So we want to try to reduce the number of multiplications. And there's even for multiplying a 2x2 matrix by a 2x2 matrix, there's this well-known, normally you would think that requires 8 multiplications, and it normally does. But there's this famous algorithm called the Strassen algorithm, which can do it in 7 multiplications. So it basically trades off additions for multiplications. And so what they're trying to do here is for larger matrices, like a 5x4 times a 4 times 6 matrix or something like that, try to come up with algorithms that will do the matrix multiplication more efficiently. We'll do it with fewer multiplication steps. So here, basically, what they do is you start with, say, a class of so basically we want to do, say, 5x5 by 5x5. And what we're going to do now is find one algorithm that handles all pairs of 5x5 matrices. So you get one algorithm. So they have to run this thing for a long time. You specify 5x5 times 5x5. Then you run this algorithm. Maybe you run it for a day. And that will, you run this AlphaGo algorithm. And in the end, what it does it gives you an algorithm. It gives you an algorithm, hopefully with fewer multiplications than what we normally have in the default case. And so the idea, very quickly, is to find a low rank. So what they do is you can express the multiplication, the matrix multiplication requirement as a tensor, as a 3-dimensional tensor. And in that tensor, it's only ones and zeros. So and then what we can do is the goal then is to try to any tensor can be decomposed into a sum of outer products. So you have three vectors in this outer product because it's a three-dimensional tensor. And so when you decompose it as a sum of these outer products, it turns out that you can easily see that the number of multiplications is the number of terms in the sum. So there's one multiplication for each term in the sum. And so therefore, the idea is to try to find the decomposition which has the lowest number of terms in the sum. So this is called the lowest rank in linear algebra terminology. So the lowest number of terms in the sum. And once you do that, if you can do that, then you have found an algorithm. If you can find, for example, the decomposition with the minimum number of terms in the sum, then you have found the optimal algorithm in terms of number of multiplications required. And so this is a combinatorial. Finding this decomposition with minimal rank is a combinatorial NP hard combinatorial problem. And so basically what this algorithm is doing, which they refer to as alpha tensor, what alpha tensor is doing is basically a heuristic for solving an NP hard problem. And but it worked quite well, and it was able to find new algorithms for several different classes of important matrices. So that was recently published and received some attention. And the techniques they use is very similar to AlphaZero. There's even Monte Carlo tree search embedded in here. And what you do is you're playing a game, and you have your original tensor here, which is again this tensor of zeros and ones, and you want to get it down to, you want to subtract out these outer products, and by subtracting them out, you get new tensors, and you want to subtract out as few as possible to get to the zero tensor. Well, anyway, we won't get into that right now. If anyone has any questions, I'm happy to talk about it later. Okay, last example of this here is ChatGPT. I think everyone has heard about that because that's been in the press like every day for the past few months. Now, so this also uses reinforcement learning. So it's probably a very important, it's not the only thing that's in there, but it's probably a very important factor. So we all know that what ChatGPT does is it inputs a prompt and you get a response, like an essay, for example. And it has a transformer backbone with 350 billion parameters, and it's pre-trained as a language model of tons and tons of data, mostly coming from the internet. And so that's that. So that's the GPT. That's the GPT-3 model here. So we have GPT-3 model. Now, how do they go to what they're using now, ChatGPT? Well, they do two additional steps. One is they have the original parameters that they get from the language model, and now they're going to fine-tune those parameters using imitation learning. I'll say a few words about that in a second. And the second thing to do is they further fine-tune those parameters. They modify those parameters a little bit using reinforcement learning. So for the imitation learning, what they do is they actually just get humans. So they have humans. They give these humans a bunch of prompts, and so they might, if they recruit any, if they recruit any of us, they give us a prompt, and then we have to write an essay for that prompt. And then they give us another prompt, we have to write an essay, and then they'll do that with lots and lots of different humans. And that is and then they'll use that to fine tune. So then they just use that as supervised learning, starting with these initial parameters that they get from the language model, and they'll modify those initial parameters a little bit in order to push the language model to give results that are closer to what the humans gave. Right, so they're gonna model to change the parameters to push so that the results are closer to what the humans gave. So that's the first step. Then in the second step, what they do is, since it's a language model, you can sample it from it, and you can get many different responses. You don't just necessarily just get one. So you can sample from it many times and get many different responses. Then they then go to human beings and they ask the human beings to rank those responses. So for a given prompt and a given response, the human beings will come back and say, oh, this is a good response, or this is a bad response, or this response is better than the previous one. And from that, they can build, from that, they train another neural network, and actually a separate neural network, to define a reward function. So the reward function takes in as input the prompt, the response, and then gives back a reward. And they try to train this reward function in this neural network to match the rewards that the humans gave. Okay, so they have that. So now you have a reward function, and then they can use that reward function for reinforcement learning. So now what they do is, basic idea is that they're going to further move those parameters in order to increase that reward, to increase the reward that you get from the reward function. And here this reinforcement learning problem is really a so-called bandit problem, because it's only one step. There's no multiple steps here. You're in one state. That's the state that you have from your prompt, and we're going to move our theta in order to increase the reward, and then we have a new state, which is a completely new prompt, has nothing to do with the previous prompt. So it's not a traditional sequential decision-making problem. It's more of it's a simplified version. It's a so-called bandit problem. So anyway, that was used there. Okay. So I'm going to skip over this, but it's also been used in nuclear fusion. We won't get into that right now. So just to say a few words now about some of the work that's been done in my own group. And I'm going to just briefly very, very briefly talk about three papers that we wrote over the past few years. The first one is, first of all, in many of these papers we've been using the Muchoko benchmark, which I mentioned earlier. It's a benchmark for robotic locomotion. And some of these particular environments are very challenging because the state and action spaces have very, very high dimension. So first one is randomized ensemble double Q learning fast without a model. And so what makes, when we're going to train a robot, what is very important, there's all these things are important here. But what is particularly important is the so-called sample efficiency. Because if we train a robot, if we interact with that robot a lot, we're going to wear that robot out. And this may also take a long time to find a good policy. So when you're dealing with real physical objects or mechanical objects, we're very concerned about sample efficiency. We do not want to interact with the environment too much. We want to get a good policy with as few samples, with as few interactions as possible with the environment. And so much of our research and many other people's research has been focused on coming up with reinforcement learning algorithms that are sample efficient. So, there's been a number of actor-critic algorithms. Some of you may have heard about them. There's so-called deep deterministic policy gradient, DDPG. Then there was TD3. Then there was an algorithm that was popular for several years called soft actor-critic, and that was the state-of-the-art for several years, came out of Berkeley. Then there were so-called, these are all model-free algorithms, and there was these model-based algorithms that also came out of Berkeley. They turned out to be somewhat more sample efficient, but didn't have the best asymptotic performance. And then more recently, we came up with an algorithm called randomized ensemble double Q learning, or REDQ, and that algorithm is currently the state-of-the-art for these these actor-critic situations. And so the basic idea is that in, say, SAC, which stands for soft actor critic, sort of the standard thing to do is for every interaction with the environment, every time you take an action, every time that is you push the robot once, you're going to do, corresponding to that one interaction, you're going to do one update of your Q function, of your neural networks. So you're going to do one gradient step with your neural networks. If you do too many gradient steps, what happens is that performance might increase initially, because you would think that to improve sample efficiency, we should do more gradient steps. We don't have, instead of taking so many interactions in the environment, why not just take lots of gradient steps for every one action? Maybe that would give us a better result. But it turns out that that doesn't work. It works a little bit at the beginning, but then if you keep on doing it, you get very, very bad performance. This is the original SAC performance, then we get some improvement, and then if we keep on doing it, this shows here that we're taking 20 gradient steps for each environmental interaction, it will go down. So, so people were sort of stuck that way, and we looked at this problem too, and we found that by making some changes to the SAC algorithm that are just small changes but non-obvious changes, then you can get much better performance. And the basic, basic idea, first of all, was to use ensembles, because the problem is that when you are taking many gradient steps for every, then you run into a potential overfitting problem. So we're going to update. We are going to take many gradient steps for every environmental interaction. We're going to take just G value that we use is roughly on the order of 10 to 20 gradient steps per environmental interaction. The default net number for n is 2. SAC uses 2. We use a much larger value for n. And then what's very important is that when we calculate the so-called target, for those of you who are familiar with this kind of thing, when we calculate the target, we can use all n Q functions in our ensemble. But if we do that, we're going to underestimate our Q function. If we only use one Q function, we'll overestimate our Q function. If we use too many of them, we'll underestimate, and we have to find just the right number. And so we leave this as a parameter m. Turns out that the magic number is 2, and then things work out. So with that algorithm, then we were able to get much better results. And so, for example, this is SAC uses 4 different environments: Hopper, Ant, Walker, Humanoid. This was the state of the art from Berkeley, SAC. And here, this is an algorithm. This is the best model-based algorithm. And this is our algorithm here, RegQ. And we can see that RegQ, does much better than SAC in the early stages of training. And then in late stages of training, it does much better also than the model-based approaches there. So since then, Berkeley they have seen our work, and now they're actually using our algorithm to train not simulated robots, but real robots, because this algorithm RegQ is now efficient enough that you can go back and actually train real robots directly without having to even bother with any kind of simulated environment. So this is one paper that they have there. Okay, I'm just going to talk very briefly about 2 other pieces of work. One is, this is more of a theoretical study that we've been interested in. There's an algorithm called Monte Carlo exploring states. And this algorithm you can find in the classic book on this is not deep reinforcement learning, this is just ordinary reinforcement learning. And you can find this algorithm in the classic book by Sutton and Bartow. There's one very classic book on reinforcement learning by Sutton and Bartow, and he has, in there they have this algorithm. And at the end of that, after presenting this algorithm and talking about all its nice properties, he says that the biggest open question in their view, and biggest open theoretical question in reinforcement learning is to prove that this algorithm converges to the optimal policy. And a lot of other people are interested in things like regret analysis, and that's important, but just here in this case, just proving convergence is not obvious. So, so this algorithm, what is it about? It's a very simple algorithm. But basically, the algorithm is that what we're going to do is we have our current policy. We run an episode. After we run that episode, we get the return, and we take those returns and we average them in with other returns that we saw previously to estimate our Q function. So we're basically, it's just, we're just running, we have our policy, we run episode, we see from certain states, we see returns, we take those returns and we average them in from the other returns, with the other returns that we've seen from those same states. And then that's our Q function here. And then we're gonna get a new policy by doing the same old thing that we always do with the Q function. Let's take the argue max. So it'll give us a new policy, then we run again episodes, and with those episodes, we're gonna update our Q function and then repeat the process. And the way exploration is handled is that at the beginning of every episode, we start in a different state in action. We randomly choose the state in action at the beginning of every episode. And so this is a very natural algorithm, and there was no proof of convergence. And what we were able to do is for a fairly large class of MDPs, but not for all MDPs, we were able to prove convergence. And we were also able to show that for some we came up with a counterexample for an MDP outside of this class, what we call OPFF, convergence doesn't occur. So what we learned in this research was that that it doesn't in general converge, but it does converge for many important MDPs. So that was one thing, and we're still working on this problem actually. So and the proof is actually quite simple. It's not that often when you have these kind of convergence proofs, you have to use things like stochastic approximations or martingale theory. We didn't have to use that at all here. We just have to use law of large numbers in an inductive argument. So the proof is pretty straightforward. You could teach it in a master's class without any problem. Okay, and so the third project I'll just briefly mention because I'm running out of time is having to do back to deep reinforcement learning, and the red Q algorithm that I described earlier is a so-called off-policy algorithm. In reinforcement learning, they talk about off-policy algorithms and on-policy algorithms. On-policy algorithms means that when you do your update, you only use the data from your most recent policy. So you only use very recent data. Off-policy algorithm means that you can use any data whatsoever. You can use data that you got from policies a long time ago to do your update. Off-policy algorithms tend to be more sample efficient, but on-policy algorithms tend to be computationally less expensive. So now in this problem here, we're looking at a problem called a constraint problem, where we want to maximize the discounted return, but we have a constraint, and here we're using discounting as well, where we have a discounted cost, and we want to make sure that the discounted cost is less than or equal to B. These class of problems in the reinforcement learning literature are often referred to as safety problems. Like this might be a safety constraint. So you want to make sure that, for example, that that GDP is high, but inflation is not is bounded, for example. So anyway, so this is the class of problems that we're looking at, and in the on-policy world, even without constraints, the most famous algorithms that you may have heard of are policy gradient, TRPO, and PPO. These are three very popular algorithms. And TRPO and PPO are so-called trust region approaches. They continue to do updates with recent data as long as policy doesn't change too much. So what you do is, without getting into the details, is we're going to have our recent data. We've run a trajectory. We've run an episode with our most recent policy. We get data. And using that data, we're going to do updates. And we're going to keep on doing updates and updates and updates. But when do we stop? We're going to try to measure how far away our new policy is from the previous policy. When it gets, and as long as it remains kind of close, we'll continue to do updates. When it gets too far away, we're going to stop and collect more data with the new policy. And the way they measure whether how close you are to the old policy is using the KL divergence. So in TRPO and PPO, they both use this idea. So we're going to just keep on updating as long as the KL divergence is below some hyperparameter delta. So there's a group of researchers coming out of OpenAPI actually, and they did some fundamental research on this constraint problem, and they argue that the constraint problem can be approximated by this problem here. So, and again, what we're going to want to do, so the situation is that our current policy is theta k, and we want to find a new policy theta k plus 1. So what we're trying to do is find a new policy theta, and this is basically optimizing the return, and this is basically making sure that our constraint is less than or equal to b, and this constraint here is making sure that our new policy is not too far away from our old policy. And the way they solve it is they work in the parameter space, and they get second order Taylor series approximations of all these guys here. And then you can solve in closed form, because it turns out to be a convex optimization problem. You can solve for the optimal theta, but that optimal theta involves a so-called Fisher information matrix that you need to invert. The Fisher information matrix is a dimension, the number of parameters you have in your neural network. So as you can imagine, that is extremely difficult to invert. And so they have to use conjugate gradient approximation methods. So anyway, this is their approach. It's a well-known approach. It's kind of messy. It has lots of approximations in it. And so what we did was our approach is to instead try to find the optimal policy in the non-parameterized setting. So forget about the neural networks. Try to find the optimal policy in a non-parameterized setting. Project the optimal policy to the neural network, because in the end, we're going to need to have a neural network here. And then this is going to lead to a first order algorithm circumventing the inversion of the Fisher information matrix. And this very quickly, how's that done? So here's the same problem, but now we remove the theta. So it's a non-parameterized version of the problem. So we remove the theta. And so we have this one theorem that the optimal solution, this actual non-parameterized problem, has a nearly closed form solution. And that we can get this from sort of optimization theory and duality theory. And it takes this form, but it involves this kind of normalization constant. So it's not fully closed form. It's not fully closed form, but so we can't really just use this. One might think, oh, maybe we can just use this policy now since it's the optimal policy. But since we can't really sample from it because we don't know the normalization constant, we can't really use this directly. So what we do anyway is we take this structure, and now we're going to project it back to the neural network. To project it back to the neural network, we're basically going to use KL divergence and try to find the theta in the neural network that's as close, such that pi theta is as close as possible to pi star. So that's what we're going to do here. And when you do that, the mathematics works out quite nicely, and it leads to an algorithm that I'm not going to describe here because obviously it has many lines of code. But just to give you the results, we're basically, for example, comparing our algorithm, which is the blue one, to, for example, the previous state-of-the-art CPO. It does much better here, for example. And the green here is compared to PPO. It does also much better than PPO. This is what we're showing here is the reward, and this is what we're showing here is the constraint. And some of these algorithms don't actually even meet the constraint. Most of them do, but not all of them. And in general, though, we see that our algorithm is doing better than all the other algorithms. So, so that's that. Just one last slide. Just some of our current projects that we're looking at. So we're looking at this proof of MCES. We believe that if we make a very minor modification to the algorithm, then we will be able to prove convergence for all MDPs. So that's one thing we're working on. We're almost done with that, I think. And another thing that we're interested in is, I don't know, how many of you have heard of the decision transformer? Has anyone heard of that? This is more specialized. Anyone hear that, decision transformer? One? You heard it? Great. Okay, this is one person. So anyway, this is kind of a hot thing in reinforcement learning now. And it's using transformers to generate episodes. And we have some ideas about showing that this kind of approach is equivalent to something else that we worked on in the past. We've been working on using reinforcement learning for simultaneous machine translation. So simultaneous machine translation is when, like, as I'm speaking, if there's someone in this room who's at the very same time translating what I'm saying into Arabic, for example. So if there's someone who is, in the middle of my sentences, not waiting for my sentence to complete, just jumping in. That's what happens often, right, when we have human translators. And so try to get, right now, most of machine translation is about, you give it a sentence and then give it a full sentence and you output a sentence. But here we try to translate before the sentence ends, right? And this is the simultaneous translation. And you can pose this as a reinforcement learning problem. We're interested not in also, besides the discounted criterion, we're interested in the average reward criterion. And something else we're interested in, I'm wondering if how many, this has nothing to do with reinforcement learning, but we're looking at this is some deep learning problem. Neural collapse. Has anyone heard of that? This thing, neural collapse, this new thing? There's just some interesting theoretical work that's come out recently on neural collapse. Anyway, so we're doing some work there. So that's it. I want to thank you. I'm sorry if I went over schedule a little bit.
Got about 5 minutes for questions.
Is there a link in your rescue algorithm with because you have several key functions, and in distributional RL also you have several key functions. So are there like common intuitions?
Common
intuitions between distributional RL, or you're learning like several key functions?
So yeah, we're not using distributional RL here. We actually have tried that though, and we even have a workshop paper with it, and it gives very similar results. So you can take the distributional RL approach and it will give almost very similar results. Yeah, very good point.
You mentioned sample efficiency, and I've seen a work, I believe, from Berkeley when they tried to teach the robot in the real world under 1 hour, like it's a physical.
Teach a robot?
Physical, like not in the simulation, but they took the one. So I wonder if your algorithm was like test on this setting, or what do you think about this direction?
Yeah, we had never worked with physical robots. It's too challenging for us. But people who do that, I definitely admire them. But as I mentioned, the Berkeley people have applied RedQ directly to an actual robot, and they have shown that they have been able to train it they weren't able to train it using SAC because it wasn't sample efficient enough, but with RedQ it is. They can do it with RedQ. Yeah.
Yeah, for the deep reinforcement learning, how do we know that we are not violating Bellman principle of optimality when we apply the neural network there?
Well, some of the algorithms are using Bellman ideas there. So, for example, the DQN algorithm, which was used in Atari games, is using the Bellman idea, and that often is very useful because that will help us. That sometimes will lead to we'll get the result done. We'll get the job done. But violate the Bellman optimality, the Q function that we often get, in the end, after we do all this training, the Q function may not satisfy fully the Bellman equation. Yeah, sometimes I think it actually doesn't satisfy it by a large margin, but it still works. So this is still one of the mysteries of
Keith, I have a question related to the networking.
Okay.
So we used deep reinforcement learning and the dynamic programming to program the routers. So would you suggest that, and we are not getting proper results. So would you suggest that RedQ might work there, particularly when it comes to the haptic data with a very short burst of information and very low latency?
So you're programming the routers?
Yes, so we need to program the routers so that we don't get a very long delay. We need them to have a higher priority for haptic data.
Right. Maybe we'd have to sit down and talk about it.
Yeah, that's okay. Thank you.
Yeah.
One last question.
So I have a question. So you have been talking about simultaneous machine translation, and I'm a bit familiar with the problem. We have been working on that. So I'm just wondering, in your formulation as a reinforcement learning problem, what is different there? Is it that you just have one more action, which is kind of to decide when you have seen enough so that you can actually now produce? And then the other question is, can you go and correct your current translations now that you have seen a little bit more? You know, kind of you might be a little bit certain, more certain, and kind of what is difference in the reinforcement?
So the way we pose, there's several ways of posing the problem. The way we pose it is like, what happens when humans do simultaneous machine translation? Usually they don't go back and correct, right? They'll say something and then they'll continue on. They won't correct what they said before. So we try to take that same approach. So you're not allowed to correct what you said before. So the decisions to make are like, when do you start to translate? Because you have to make some decisions like, do I wait for the first token, second token, third token? At what point do I start to output? Do I have enough confidence that I can start to say something? And then you might not say, and then you might wait. So you might say a few words, and then you might wait again. And then you have another decision. When do I, output the next phrase? And so you have these sequential decisions to make. In ordinary machine translation, it's not really a reinforcement learning problem because you're just given one sentence and you really have one decision to make, which should be the output sentence, right? So that's why there's a sequential decision problem in the simultaneous translation problem, but in regular machine translation, there really isn't a sequential decision problem there. Yeah.
Actually, this is something that you can learn very well from the human interpretation. Kind of, we have been collecting this kind of data, and they have different strategies, right? So kind of, there's one thing that you do in Japanese, there's another thing that you do in German, because in German, the conjugated verb comes at the end, and when you translate to English, I mean, you really cannot translate until you have seen the verb, but it's going to come at the end, kind of, they're like starting, like making things up, kind of doing different kinds of reordering. And actually, you can correct yourself. I mean, in certain cases, you cannot do it all the time.
Yeah.
That's all easy compared to Arabic, because you can say the word and the point how you pronounce it. It might be adjective, accusative, dative, or subject. So
the other thing, I know we are over time.
Sorry.
The other thing about even like the traditional machine translation, I mean, I get the point about, okay, it's not sequential in that sense, like similar to simultaneous, but the way people do it these days is that, when you are generating, you generate like one token at a time, and it's like whatever you will do next is actually dependent on that token that you just generated as well. So there's a little bit of kind of pseudo sequentiality there somehow.
Yeah, so people have tried using reinforcement learning for those autoregressive models. So you'll see that in the NLP papers, they talk about policy gradient and stuff, and use some of that stuff in there. Yeah, but fundamentally, it's not really the sequential decision problem. But
But it could be a chain of Markov processes within the whole sentence.
Right. Yeah, that's what saying here. Yeah.
Okay, we're going to have to finish up there. So thank you. Join me again in thanking.
Thank you.